The dynamics of vertical circular motion for, say, a ball on a string swinging around like this are relatively simple if we confine ourselves to points like A, B, and C. But if we look at some arbitrary point on the path, like when the ball is here, we have to work just a little bit harder. And we can see why, because of our second step, AAA, our axes at this moment are not aligned with one force in particular, the force of gravity. Now, tension, of course, points directly in towards the center of the circle. I haven't even drawn it in this case. I've left it out because I want to focus on the force of gravity. Tension lines up with our r hat direction, our radial direction, but gravity doesn't. So for this step, we need to break up gravity into its components. Break up gravity into a component along the radial direction and a component along the tangential direction. So let's see here. I want to make the force of gravity the hypotenuse of a right triangle with one leg parallel to our tangential direction and one leg parallel to our radial direction. I'm going to draw that triangle there, and I might actually draw that triangle here as well, so we can see it on either side. Now the legs of this, or the sides of this rectangle I've drawn, the sides represent the components of the force of gravity. This here will be the component of gravity in our tangential direction, FGR. We see it pointing in the negative tangential direction right there. And then this will be, oops, that should have been FGT, tangential. And then this is FGR right there, the component of gravity pulling in the radial direction. We have had to break up gravity into components because it did not align with the axes that we chose. So next will be to do a bit of geometry. I'm going to define an angle theta right here, such that theta is 0 when the ball is at point B. And then theta will be pi over 2 when the ball is at point C, and theta would be negative pi over 2 or 3 pi over 2 when the ball is at point A. So I'm going to define that angle there, and then do a bit of geometry here. Remember our congruent angles. And note on this picture that if this angle is theta, then this angle here would be congruent to it. That would also be theta right there. And so I can express FGT, our tangential component here in the negative tangential direction, the part of gravity that will be slowing the ball down, the part of gravity contributing to the tangential acceleration, which we know changes the speed of the ball. That looks like it can be expressed as mg cosine theta. Whereas FGR here, the component of gravity that's helping turn the ball, contributing to that centripetal acceleration, helping change the direction of the velocity. I know that that side FGR is the same as a length as this side right here, so it can be expressed as mg sine of theta. So there we go. We just need to break up gravity into these two components, mg cosine theta and mg sine theta, and now we can set up N2L over again. So in the radial direction, we sum the radial forces over the mass. Of course, we have our tension pointing in the negative radial direction, which I didn't draw this time. So, but we know it's there, the minus Ft, and then minus FGR, our radial component of gravity pulling inwards. So it's minus Ft minus mg sine theta. And then this is the equation you would typically be rearranging to solve for something. Then in the tangential direction, tension never has a tangential component, but gravity sometimes does. At this moment it does, mg cos theta, and it happens to be pointing in the negative tangential direction, slowing us down opposite the velocity at that moment. So minus mg cos theta. And we see that the masses would cancel out. So it's minus g cos theta equals our angular acceleration alpha times r. So that equation we might be rearranging to solve for something of interest. Okay, and you can verify that if you put in these specific values for theta into the sine theta here and the cosine theta there, we can recover this set of equations that we worked out from just considering points A, B, and C. So we still have these results sort of contained as special cases of this more general and more powerful result.